Okay, the rest of them should be coming really quickly. Like I said before, the problems that are in your notes up to this point, I've actually done the workout problems for you on the day before this day. They're all worked out, so try them, see if you can do them. There will be problems like that on the test, so I wanted you to make sure you had a practice one that you could go through and do. Okay, so this balloon riddle. I have two balloons here. They're both full of different amounts of air. This one doesn't want to stay on there. There we go. Oh, whoops, that was good. Okay, we're just going to hold this on. One's big, one's small. I've closed the valve in between them. What do you think is going to happen when we open the valve? This has to do with pressures. Think they'll equal out? Okay, there's some things that we can say that they might do. They might do like A, this balloon will get smaller. It could be like B, they'll equal out. Or it'd be like C, well, if I'm doing it this way. If it'd be like C, this one would be smaller. What do you think is going to happen? For the balloon riddle up there, my one on the left is pink and my one on the right is blue. How many think it's going to be A? Raise your hand. Make a commitment. How many think it's going to be B? How many think it's going to be C? Okay, I'm going to, let's have you open the valve, you play with the balloon. You open the valve, you play with the balloon. Okay, ready? Go. Play with it like squeeze it. Squeeze it like you're trying to get the other person to lose. Okay, what's happening? Talk to everybody. So leave it open all the way. There we go. That's open. The small one's getting smaller. Megan, come on, push. It's going to pop anyway. Okay, why do you think that happened? Okay, I'm going to show everybody. We opened it up. And Megan said she was trying to squish it. You guys want to try? See if you can fix it? Is it changing?
No.
It's not changing. Okay, why did the smaller balloon get smaller and the bigger balloon got bigger?
Less pressure, less air.
Less pressure, less air. Have you ever blown up a balloon? When's the hardest part to blow it up? When it's small, right? When you first begin. Why? Because the latex is tight together and you've got to stretch it out before it's easier to blow, right? Okay, so that's what's happening here. We're working with pressures. And we're looking at what's going on in the outside. Okay, so as we look at the pressures, oh, come on. Okay, when a balloon is being filled, the pressure inside is greater than the pressure outside. When a balloon is filled and tied, the pressure inside and outside are equal. When a balloon deflates, the pressure outside is greater than the pressure inside. So we have intermolecular forces now that we're going to head into. They're also part of this chapter. There are three main ones: London dispersion forces, dipole-dipole, and hydrogen bonding. London dispersion forces are considered the weaker one, except when the molecules are so different in size. If they're very, very different in size, extremely different in size, London dispersion forces can overcome. But London dispersion forces are sort of like the glue that holds everything together. They're in everything. Dipole-dipole, anybody know what a dipole is? A dipole has a positive side and a negative side. And so it's saying that they're sort of like poles, and they're sort of hooked together with poles. And then hydrogen bonding is with hydrogen, of course, but it's only with nitrogen, oxygen, and fluorine, so NOF at the top there. And we'll go into each one of these a little bit more. So depending on the strength of each of these bonds, that depends on if a compound has high or low melting point or boiling point, if it's a solid, liquid, or gas at a given temperature. London dispersion, yep, we need to go back. Okay. While you're doing that, would you put your, I forgot to stamp your lab for pre-lab. So if you put your lab out, I'll just stamp it as long as you've got it done for pre-lab. Okay. Still got my Christmas stamps out. Sorry, guys. You're going to get a Christmas stamp. Did you get yours done, Megan? No. Okay. All right, we ready to move on? Okay. So, London dispersion forces. I like to think of this like London fog. If you've ever been to London, it's everywhere in the morning. It's just there. It's something they expect. Okay? It is, to explain it, it's basically every molecule or every atom has electrons running around it. At one point in time, there might be more electrons on one side of the atom than there are on the other side, just because it's a random thing. Because of that, they have what they call an instantaneous dipole. So for just a second, there's a positive and a negative side. And that's enough to hold things together. Okay? All compounds we have exhibit London dispersion or just dispersion forces. The larger the molecule, the larger the attractive force, and the stronger the intermolecular forces. Okay? But just remember, London dipole or London dispersion forces are momentarily changes in density of the electrons. It's just a second where it creates a dipole, just for a second, and then it's gone. Because those electrons are zipping around the outside of the atom, and sometimes they end up on one side than the other side. Okay? So if you look at it like this, this would be an example of a dipole. If you look in and divide the molecule in half here, you can see on this side we have a little bit more electrons than on this side. So just for a second, we have more electrodensity on that side, creating a slight negative. And we have less electronegativity on that side. That force between those two atoms is what we call London dispersion forces. Okay? Does that make sense? Everybody understand that? It's sort of a little bit rough. Okay? Stay, go back. So I wanted to make sure you had a picture in your mind of how that looks, because saying it out loud and actually seeing it, a lot of people are more picture. I like to see things rather than just write them with words. Now that's instantaneous. That's not going to stay that way. Okay, so that just happens to be those electrons are zooming around, and at one point in time, more of them are on one side than the other. So it's instantaneous, and then it's gone. We okay? All right. So going forward, the next step is dipole-dipole. This is where I actually can write the equation of something and say, you know what? Hydrogens usually take a positive charge, and oxygen usually takes a negative charge. So overall in this molecule, I'm going to end up with a slight positive on this side of the reaction, or molecule, and a slight negative on this side. Because of that, we have a dipole. In other words, we have a positive side and a negative side for the molecule itself. And they line up, positive, negative, positive, negative. Water does this. Okay? We have two polar molecules, and they stay that way. It's not instantaneous like London dispersion forces. It doesn't go away. It stays that way. Okay? So this molecule right here we have is formaldehyde, also known as methanal. All right, the last one is the highest form, is hydrogen bonding. And that only occurs with nitrogen, oxygen, and fluorine. So if you look at the top row, before you get to the noble gases, it's NOF. So nitrogen, oxygen, fluorine directly connected to a hydrogen will cause what we call hydrogen bonding. And there are actually arguments right now that say hydrogen bonding should be another type of bonding, just like ionic and covalent are bonding, because it is that strong. but there's no real actual bond between the two molecules. It's just a real strong attraction. So there's an argument on both sides. Water is one of the ones that we see that does that a lot. The hydrogen side of the water will be attracted to the oxygen of another one. And it actually forms a grid in which when we get ice, it actually expands because it has to be a certain way when it freezes or goes to a solid. So these are the strongest types of the three intermolecular forces. This intermolecular force of hydrogen bonding is used in our DNA, and it's in several bonds between adenine and thymine, between guanine and cytosine. It's what helps hold together our base pairs, and it is so strong that it's almost like a real bond as you do the DNA helix. Okay, so basically, overview. Yes, real quick, yes. DNA helix. Okay, so on this one, intermolecular forces, this is just a summary. So the type of force, London dispersion, relatively weak. It's in all molecules. An example of one I showed you was the CH4 molecule, but you could do C2CO, which is formaldehyde. It's in all molecules. It doesn't matter which one you choose, but it is in all molecules. Dipole, you have to have a set dipole. It doesn't just instantaneously appear and then disappear. It's set. So that would be like our formaldehyde or methanol, or our water is also a permanent dipole. But water has something else that the others that we had above that didn't. It's called hydrogen bonding. So water actually has London dispersion, dipole, and hydrogen bonding all occurring in that one molecule. It's molecules only with nitrogen, oxygen, or fluorine directly connected to a hydrogen. And if you just remember, it's that top row of the periodic table before you get to neon, those top three, NOF. So like the Hof Festival, NOF. Okay? We got it down? We good? All right, going forward. So intermolecular forces affects our boiling point and our melting point. Boiling point is a temperature at which liquid is converted to a gas. Melting point is the point at which you change a solid to a liquid. The stronger you have an intermolecular force, the higher the boiling point, because it doesn't want to go to that next state. So compounds with only London dispersion forces are very low boiling point. As you add into it dipole, they become a higher boiling point. As you add into it hydrogen bonding, it becomes the highest boiling point. You will need to be able to look at molecules on the test and be able to pull out which ones are the lowest, which ones are the highest. Weight does matter too. So if I have a bigger molecule, it's going to take more energy to get it into a gas or a liquid. You good to go? No? All right. So as we look at this, if we just take these two, methane and water. Methane's boiling point is a negative 162. Its melting point is a negative 183. It weighs 12, 13, 14, 15, 16, about 16 grams per mole. Water, on the other hand, it's 16, 17, 18, but its boiling point is 100 and its melting point is 0. It's higher because it has dipole, it has hydrogen bonding. So you can see that the difference in those two just immensely. Okay, so let's look at some others. Let's look at these. Look at the difference in boiling point for these two. On these two, the larger molecule has stronger forces. even though there's no dipole-dipole, there's no hydrogen bonding, but because butane is a bigger molecule has more electrons, a chance of more electrons being on one side than the other, therefore it has higher London dispersion forces, therefore the boiling point and melting point are higher than propane. Okay? So the mass matters. Well, it's really not mass, but the number of electrons. Okay, so liquid state, vapor pressure. This has to do with vapor pressure. So evaporation is the conversion of liquid into gas phase. It's endothermic. It takes energy from the surroundings. Condensation is going reverse, so we're cooling it down. It's giving off heat. All right, so when we talk about vapor pressure is the pressure exerted by the gas molecules above a liquid state. Vapor pressure increases with increasing temperature. So if I have pop bottles, for instance, and I'm worried about that vapor pressure above the pop, if I have warm pop and I open it up, what happens? Nobody's ever opened up warm pop before? It fizzes everywhere. That's because there's more gases above. If you cool the pop down, though, and then open it, it doesn't fizz quite as much when you open it because the vapor pressure is lower. The boiling point of a liquid is a temperature at which the vapor pressure equals the atmospheric pressure. For us, the atmospheric pressure is not 1 atmosphere. So when we do our labs and we're trying to figure out what our boiling point is, we actually do have to boil water to find out what water boils at, because it's not 100 here. It's less than 100. So we have to figure that out because our vapor pressure is not 1 atmosphere or 760 millimeters mercury. Whoops, I think I passed one. Yep. Okay. So liquid state vapor pressure. To have a high vapor pressure, you're going to have weaker intermolecular forces, or you're going to have it at a very high temperature. If molecules are allowed to escape into a gas, then we get a high vapor pressure. A low vapor pressure is when we have strong intermolecular forces or we have a lower temperature. Not very many gas molecules are allowed above. So when I was talking about the pop, the same thing here. Okay? So stronger molecular forces, if I'm looking at a same temperature, they're going to have a higher vapor pressure. As we look at the liquid state, a lot of this you already know, but viscosity. Viscosity is how fluid flows. It's the resistance to flow. So if you compare just pouring water compared to pouring honey, the water is going to flow being very quickly, but the honey is going to be more have a higher viscosity. It's going to be thick. Compounds with strong intermolecular forces tend to be more having more viscosity. Substances of large molecules tend to be also more have more viscosity. So if you think about it, like Crisco has a very high viscosity. It doesn't like to flow at all. Okay, but you look at oil, which is smaller by far, then it flows a lot better. All right, so liquid state. In a liquid state, when we're looking at water, what's happening is, have you noticed water bubbles? It actually makes little bubbles when you pour things, but if you pour like oil, it doesn't. The reason why is it has hydrogen bonding that's pulling it at all different directions. And so it actually forms this bubble. And you can actually take and put several drops of water on a penny to the point where it looks like it's got a bubble head. But if you try and do that with oil, it just stays flat. It never bubbles up. And because of this, it ends up with what we call surface tension. And you can try this at home. Try and actually float a paper clip on water. It will float. And a razor blade will float. Okay? So you can actually get it so it holds it up. This is what water skiers use to walk on the water. That's sort of their little thin layer. So when they're pushing down right here, their weight is not big enough to break that intermolecular force. It sort of bends it a little bit, but it still is enough to hold them. Okay? All right, so when we look at viscosity and surface tension, the stronger the intermolecular forces, the stronger the surface molecules are pulled down towards the interior of the liquid, and the higher the surface tension, so it can hold things up. Water has a very high surface tension because of its intermolecular hydrogen bonding. When small items seem to float on the water surface, they're held up only by surface tension. So if we tried to put the same thing on oil, it probably would fall. We good? Can't remember how many things I had you fill out. This one sort of creeped me out. Spiders can also walk on water. All right, so we're going to do a little surface tension experiment here. So I'm going to pass out, if I could have one, well, each of you come up. One of you grab a plate and a cup of water, and the other person grab a toothpick and one of each of the colors right here. And then we'll do a little experiment. So I've got 1, 2, 3, 4, 5, we'll call it. So I'll put you two as a group. Okay, come on up and grab. I'm going to pour some milk here. Tried this on my grandkids over the weekend. They had fun with it. When you get back to your area, carefully pour the milk into the plate. I need one more. Okay. We need one more. Okay. Okay, once you've got the milk poured into the plate, I want you to take the colored food coloring and put one drop in a triangle. So one drop of red, yellow, and green. So put it in a triangle, far away, closer to the outside. Okay? So you're actually going to, here's your plate, you're going to put a drop of green, drop of red, and my yellow is going to have to be blue because I don't have a yellow. Okay? Like that. Make a triangle. Just one drop. And then you can bring back up the food coloring if you want to, or just wait until you're all done. Okay, now you have your toothpick. Your toothpick was put into dish soap. Now the dish soap milk has water in it. And the dish soap has an ability to break the surface tension. So go ahead and put that toothpick, the dish soap end, right in the center. And just watch what happens. You just need a little. Just put it down in. Just hold it there for a minute and wait and watch what happens. So what's happening? It jumps away, and then if you're sitting there holding it, what's happening? What's coming up? What happens to the colors? They're coming back, aren't they? Where are they coming back? In the center. So they're like going down underneath and coming back up in the center, hopefully. Yours goes for a minute. This group over here is challenged. You know, huh? Okay, so this is an experiment in surface tension where you can see what happens when a surface tension is broken and it actually can move around. With regular surface tension, it would hold it in the place. Now go ahead and just move that toothpick around in different spots. See what happens to it when you move it in different spots. When you get done with playing with it, go ahead and dump the milk into the sink and then throw the cup and the plate away and bring me back up my food coloring. So that was a little brain break for you. Hopefully that was sort of fun. Just be really careful carrying it, because it'll make a mess if we spill. So don't rush around these people. They're going really slow trying to not spill. If you need some paper towels, I do have some up here. I don't know what happened to our blue, but our blue disappeared, so. All right. So we're going to go ahead and get started. Hopefully, I'll wait. Don't hurry. I don't want milk spilled on my floor. Okay, let's go forward. The last thing we need to talk about is solids here. Solid states can be crystalline or amorphous. This is something new. You've heard of a solid as a solid. You've not heard of amorphous, I'm guessing. Crystalline, maybe, but not amorphous. So let's go through each of those. So crystalline is where it sets up in a specific order. The atoms sort of vibrate in place. They have a specific way they go. Amorphous, they're more random in arrangement. There's not a set way they actually go together. They just sort of are there. Okay? So let's go a little bit more into it. Amorphous solids have no regular arrangement of its close packed particles. It's like cotton candy. Okay? It's like a rubber eraser. Those are amorphous. Okay? Those are some examples of amorphous. Crystalline is more set. That's like glass or rubber. Amorphous solids have no regular arrangement because they cool too quickly. They're not allowed to get into a specific arrangement. Okay? We still got amorphous over there. Sorry, I thought we were crystalline. We're still amorphous. So glass is considered amorphous. If you look at really old Pioneer glass, it's thicker down at the bottom than it is at the top. That's because it never fully sets. It keeps moving very slowly, but it does. They sort of fold and intertwine and become together. Okay, we okay to move forward? No? Okay. Crystalline solids are where we have our ionic and our molecular solids. So like table salt, that would be a crystalline. Water as ice is a crystalline because it arranges a specific way. Right. Network solids. So we have actually 4 that we were supposed to be talking about. Let me go back really quickly. Within crystalline, we have the ionic solid and the molecular solid. And then we have the network solid. That is like diamonds are network solids. Metallic solids are like any metal. So metal crystals. All right, then we get to specific heat. We're going to be doing that part of the lab next time, so we're going to go into this really fast. A specific heat is basically how much energy does it take to raise 1 gram of whatever substance I've got 1 degree Celsius. Okay, metals have very low specific heat. Water has a high specific heat. We're going to be doing metals and water. Okay? In the specific heat, basically specific heat is equal to heat divided by the mass times delta T. The equation that I gave you in your lab is Cp equals M, joules, or heat, is equal to M Cp delta T. M is mass, Cp is specific heat, and delta T is change in temperature. And we're actually going to be heating up metals in a beaker. So we're going to weigh the metals, put them in a beaker, heat them up. Once they're heated, it doesn't really matter how much water's in that because I'm not measuring the amount of heat of the water. I just want the water heated to the metals heated to the same temperature as the water. But in a styrofoam cup, I'm going to put 100 milliliters of distilled water so I know how much exactly water I have. I'm going to weigh that, make sure exactly it's 100 grams or whatever it is. I'm going to use it. Then I'm going to move the hot into the cool and see how much the temperature changes. And then I'll move the second one and see how much the temperature changes. That's how we're going to determine specific heat because I know how much the water can give out. Okay? You have a list like this in your lab where you have how much aluminum specific heat is and how much copper's is. We didn't do gold because I'm not going to give you gold or mercury. Iron, I think, was one of them. And I gave you water, and water was 4.184. So if we were to try and calculate how much heat a pot of 1,600 grams of water took to get from 25 degrees up to boiling, we would identify, first of all, our unknowns, because it's just a story problem again. So I've got my mass, I've got my first temperature, I've got my second temperature. If I take my second temperature minus my first temperature, I can find out how many degrees I need to heat it, which is 75. The specific heat of water, if I use calories, is 1 calorie. If I use joules, it's 4.184. Okay, so depending on what you're asked to find it in, depends on which specific heat of water you need to use. Might be a good thing to put in on your card. Okay, the nice thing is that specific heat for water is also the conversion basically between a calorie and a joule. Because remember, 1 calorie is equal to 4.184 joules. Okay? So then we just plug it into the equation that we know. Is it okay to go forward? No? So the lab that we do next time will take a little bit more time because we've got to heat up water. So I want to make sure we get as far as we can here. So if you want to go back and try some of the problems, if you want to take a computer back there while you're waiting, twiddling your thumbs, you can use it to do your Learn Smarts, whatever. Okay, so you're just going to plug it into heat is equal to mass times delta T times specific heat. That's the equation that I gave you in your orange sheet. Okay? So here, since it's just 1 calorie per gram, we're going to put our change in temperature and our mass. We're just going to times them together. Boom, we've got the answer. Okay? Now in lab, we're going to set the amount that the water heats up equal to the amount the heat of the metal loses so that we can find out what the specific heat of the metal is. So we're going to set them equal to each other because what one loses, the other one has to gain. And usually we don't write the ones down here. We just put calories, grams, degrees Celsius on the bottom, right? Okay, so converting from a solid to liquid, we all know this. We've learned this from Itsy Bitsy, right? It's freezing if it's going from liquid to solid. It's melting if it's going from solid to liquid. But that amount of energy that it takes to melt 1 gram or freeze 1 gram is known as the heat of fusion. And we'll be using that. So that energy is called heat of fusion. Okay. So here's an... Okay. So here's an example of a heat of fusion problem. So how much energy and calories is absorbed when 50 grams of ice cubes melt? The heat of fusion of water is this. So basically, I've got some grams, and if I notice right here, the units on my heat of fusion are calories per gram. So what do you think I need to do? I've got grams and I've got calories per gram. Times them together. That's it. So I'm just going to times them together. Because when I do, grams here and grams here will cancel out, leaving me calories, which is the amount of energy. Right? So I'm going to plug them through. I could set up different things right here, not a big deal. I can just look at right here. I want calories. Calories is already on top, so all I have to do is times the two together. Okay? And we're done. So usually when you're doing heat of fusion, and we'll talk about heat of vaporization, which is basically liquid to gas and gas to liquid, same thing. All you have to do is make sure the units will cancel. So if they give me kilograms and heat of fusion is in calories per gram, what do I need to do? Change the kilograms to grams, then times them together. Okay? If they give me milligrams, I've got to change it to grams. So just make sure the units will cancel. That's the big thing here. Okay, vaporization. Like I said, just the same thing, but again, how much does it take to vaporize 1 gram? How much energy does it take? That's heat of vaporization. And you'll see it written HVAP, and the heat of fusion will be written HFuse. Okay? So that you can tell the difference between the two. How many noticed that I put some multiple choice questions with answers at the back of this packet? Okay, those were left over from last year, but they sort of fit. I'm also still going to give you your review that I gave you, and we'll go through that. And I'll make sure this time that one of the requests was that the answers to that be up on. So I'm going to do like I did this other one. After I give it to you, I'll put the answers up on and work it through so you can see how they're done, so you can do it, look over it any time. Okay? All right, going forward. Converting a solid to a gas. This is probably something you haven't heard before. To go from a solid to a gas is what we call sublimation. To go from a gas directly to a solid is called deposition. And this one does not have a heat of vaporization or heat of fusion associated with it. We okay? All right, so really quickly, go over everything. Melting is a solid to a liquid. It's endothermic. Energy is absorbed. Freezing is a liquid to a solid. Exothermic. Energy is released. Vaporization, liquid to a gas. Endothermic. Energy is absorbed. Condensation, gas to a liquid. Exothermic. Energy is released. Sublimation, solid to a gas. Endothermic, you have to absorb energy. And deposition, gas to a solid, is exothermic, or energy is released. All right, we okay to go forward? Nope, you're still writing furiously. We'll go for about another 3 minutes and then I'll break. And you can look over lab and do whatever you need to do with the lab for today. Okay, so this should be, you should be able to think through it. If I'm getting to something that takes more energy, it's going to be endothermic. If I'm releasing energy, becoming more organized, it's going to be exothermic. So this is what we call a heating curve. A heating curve has specific parts. Anytime you have a slope, you're heating a phase. So I'm either heating a solid, heating a liquid, or heating a gas. Anytime I have a plateau where the slope is 0, I have now hit a point where I have hit a melting point or a boiling point. The first one's the melting, the second one's the boiling. Okay? A heating curve shows us overall how much energy it takes to get from one place to another. Now, that flat area still has to have heat added. I can't just say, oh, I'm now at melting point, it's going to happen like this. I have to keep adding heat until it gets all to the liquid state. The temperature will stay the same until I get past one state and into another. A cooling curve is just reversed. So I'd start at a gas and I'd come back down. Okay? So heating curve going up in temperature, cooling curve going down. So again, solid, I've got liquid and solid here, liquid, liquid and gas, and then gas. So I saw a lot of you writing that down already. I can't remember. Whoa. Whoops, sorry. This one right here, so this is a heating curve going up to gas, right? A cooling curve just reverses it, just goes backwards. So I didn't put a cooling curve on your notes, but you need to know that cooling curve is just reversed. Okay, so it's just taking this and going, boom, backwards. Okay, so I start at a gas and go down. Same kind of thing. Every flat part, just remember, every flat part, here's my boiling or my condensing point. Here's my freezing or, if I'm going the other way, melting point. Okay? This would be my delta H vap. This would be where I use my delta H of fusion. Okay? Every other state, we're going to use the Q equals mCp delta T. And the Cp will be different for a gas than it is for the liquid. It's going to be different from the liquid for a gas. Okay? All right, so here's another one, still looking at the same thing. You need to be able to say, and this one sort of put on there, the heat of this usually put the fuse there and the VAP, so you know what we're doing, because there's lots of delta H's. But it sort of tells you, you should be able to read this off. So if she asks you what's the melting point, and it had numbers here, you would be able to read it off. What's the boiling point? You should be able to read it off. Okay? If it's down here, you should be able to tell how much energy is needed to melt or boil. So what I was telling you earlier, this is what I called CP. Okay? We're going to be using that in lab. But this CP for ice is different than the CP for the liquid is different than the CP for the gas. So I could, theoretically, and actually you can do it, it just takes a lot of energy, go from some temperature down here and find out how much energy it would take to have steam up here. But I'd have to break it up into 5 different things and then add them together. Okay, you can't do it all at once. All right. Another thing we need to know is phase diagrams. Phase diagrams are another way to look at solid liquids and gases. Solid liquids and gases, always the solid will be next to your pressure or your y-axis. Always your gas will be next to your temperature axis or your x-axis. That leaves liquid in between. So if you know that, then it's very simple to find everything else. You know that between solid and a liquid, it's melting and freezing, depending on which way you're going, right? You know between a liquid and gas, it's condensation or boiling, vaporization. The one we just learned was between a solid and gas, sublimation and deposition. This triple point right here, there is a point at which the pressure and the temperature are such that all 3 states exist at the same time, solid, liquid, and gas. In other words, I can have boiling ice water. It's really cool. It's in a vacuum, but it works. This point up here, this critical point, this is the point at which past, it doesn't matter what I do, it's going to be gas. It doesn't matter how much pressure I apply, the energy of the particles are so high and so fast that there's no way I can get them to anything but gas. If I go across at 1 atmosphere, The points at which I hit here and here are what's called my normal boiling and my normal freezing point. That just means at 1 atmosphere, that's what my boiling point, that's what my melting point is. And so we call it normal. I don't know why. Everything else is abnormal, I guess. Okay, that's where I'm going to stop today. You can go, and we'll try and get the rest of it done next time. And then those multiple choice are yours to work as you need to. Okay? I'll be giving you, so next time when we come, plan on doing the specific heat part of the lab and the Charles law of the lab. Okay, because both of those were heating up stuff, and then we can put the hot plates away. Heating water. Heating water once is good. Heating water twice is not fun. All right, make sure everything's up here, and then